Hello and welcome back to Paleocast. My name is Dave Marshall and you're listening to episode 152, which is the second part of our look at Lissamphibian origins with Ben Kligman. If you've made it over from the first part, then welcome back. There's absolutely loads more to discuss. But if anyone's found themselves here, perhaps listening to the most recent episode first, then please make sure you start with episode 151, which provides all the context you'll need to understand this second part. Caecilians are a fascinating group of animals, but one that I admittedly had never heard of before. So details such as how the young of some species come equipped with teeth specifically for eating the flesh of their mothers, well, this isn't a group that I'll be forgetting in any hurry. And hopefully this isn't an episode that you'll be forgetting in a hurry either. So if you do enjoy it, please consider leaving us a rating and recommendation on iTunes, where we are tantalizingly close to being listed as a 5-star show. And finally, in the comments, I'd love to hear your opinion as to what you think might be causing this mysterious overabundance of lower right jaws of Funkus vermis. I hope you enjoy this episode. Yeah, so then something like a new fossil, a new species, could really change everything. And so when you have recently described Funkus vermis gilmori, is really going to help us understand this evolution. So, first of all, I want to know, where did the name Funkus vermis come from?
Yeah, it's kind of a different name, and the name kind of evolved through time as we were discovering the fossils, and so the field work that we did to discover this fossil or these fossils of Funkus vermis. It's done at a site in Petrified Forest National Park that we informally call Thunderstorm Ridge. And so we've been, the site was, we first discovered the site in
a thunderstorm?
Not in a thunderstorm. It was named later when I wasn't with the people who were there, but people got stuck at the site during a thunderstorm, and that's where the name came from. But we're working at this site from for the summers of 2018, 2019, and 2021. And when we're out there, it's basically badlands in the deserts of northern Arizona and in Petrified Forest National Park, where you have these rounded hills that don't have any vegetation on them. All they are is eroding rock. And we're in this quarry that's basically a big hole that we've dug into the rock where this bone layer is, and we're sitting out there for 2 or 3 months of summer, and we're basically spending all day digging, and it's hot, and we're getting tired, and so we like to play music while we're out there to kind of keep us motivated and have some fun despite all the heat. And one of our favorite genres has been 1970s funk music. And one of the songs that came on our playlist soon after we realized that we were discovering these Caecilian fossils is the song "The Funky Worm," which is by the band the Ohio Players. And the song is about a worm that lives in the ground 6 feet down, and he only comes around when he wants to get down and play funky music. And so it's just this kind of funny song about the funky worm, and it's a worm that plays guitar. And and when we started hearing the song, we were like, "Whoa! Like Caecilians are kind of like worms." And so maybe our Caecilian is the funky worm. And then we started to play the song every day that we went out to the quarry. We would play the song to give us good luck and to summon the Caecilian fossils so that we could find them. And so that's kind of where the original inspiration for the name came from. And then we kind of started thinking, oh, it'd be cool to give the genus name something like funky worm. So we contacted a colleague of ours, Ben Chrysler, who has helped us with formulating Latin words. And gave him the idea, and he came up with the Latinization of the word funk, which is funkus, and then the word vermis for worm. So Funkus vermis, the funky worm, is the genus. And kind of a fun little tidbit, but this song was the single, "The Funky Worm," was released almost 50 years ago today on January 16th, 1973. So it's coincidentally the naming of this animal after this song is on the 50th anniversary of the song coming out, and we've been in touch with James Diamond Williams, who's the last living member of the original band, and he's given us his blessing for naming the song or naming the animal after his song.
Oh, that's lovely. You haven't timed the release of your paper to the 50th anniversary, have you?
No, it's definitely coincidental. But it's a kind of a fun coincidence, though. It's definitely a fun coincidence.
Because that's the kind of thing that will get picked up by newspapers, I expect.
Yeah, definitely.
And speaking of old music, I have had, and I don't know if this is true for you and your colleagues, but when I've been writing this episode about Caecilians, I've just had Simon and Garfunkel in my head the whole time.
Oh, Cecilia.
Oh, Caecilians.
Yeah.
You live in the dark. Yeah, it's perfect. It just writes itself.
Perfect. I never thought about that. That's funny. I like that.
You never made that connection.
Never made that connection. Although I think we might have actually listened to that song out there, but we never made the connection. That's great. We're gonna have to play that one this upcoming summer now. I love that.
Everyone is going to be playing it in their heads for the next 2 days, I expect. Yeah. Welcome to my world. Yeah. Anyway, so we're out in Arizona. And we are starting to find Caecilians, or we're digging through the sediments. So can you tell us a bit about the area geologically? Like, what age rocks is it? What kind of rocks? What kind of environment did that represent?
Yeah, so Thunderstorm Ridge is in the upper Blue Mesa member of the Chinle Formation, and we have pretty good radioisotopic age constraints on the age of the Chinle and the Blue Mesa member. And so these rocks were probably deposited around 220 million years ago. And 220 million years ago, northern Arizona was located much farther south, probably within about 7 degrees north of the equator. So very different setting. Today, Arizona is a desert. Back then, Arizona was just north of the equator in the humid tropics. And there's a lot of data on the paleoclimate that shows that during the deposition of the Blue Mesa member, it was a hot and humid, high precipitation climate. And the rocks were deposited by a large river lake system that was flowing through Arizona from New Mexico, flowing northwest towards the Paleo-Pacific Ocean that would have been in Nevada at that time. And so the depositional setting is of the lower part of the Chinle Formation at that time was rivers and lakes and ponds. And so kind of lower energy depositional settings, floodplains, and the site specifically appears to be kind of a filled-in pond or oxbow lake setting where the bones of many different kinds of animals from the surrounding environments got concentrated and deposited and covered over in this possible pond bottom. And so we find the bones of animals that were living exclusively in the water, a whole diversity of different kinds of bony fish, several species of sharks, coelacanth fish are especially common. There are also lungfish. And then we get amphibious animals that were living in the water and on the land. There are, importantly to this discussion, the oldest frog fossils from North America are also found from this site, and we're currently describing those. And my research group described some slightly younger frog bones from the Chinle Formation a few years ago. There are large crocodile-like animals, the phytosaurs. There's other amphibians, importantly metoposaurs, which are they basically look like a giant 6 foot long plus salamander with a head that kind of looks like a toilet seat lid.
Oh,
And
wow.
yeah, those are particularly common in these deposits. There are early dinosaurs that are rather small. There's cynodonts, so the close relatives of the earliest mammals. Um, and kind of one of the important stories about Thunderstorm Ridge, the site that the Caecilian fossils are coming from, is that we're also finding a lot of other fossils of the earliest members of living groups of tetrapods. So some of the earliest dinosaur fossils from North America, some of the earliest cynodonts, and cynodonts that are very close to mammals. So they have double-rooted teeth in their lower jaws. We're finding these earliest frog fossils from North America, as well as the oldest Caecilians in the entire fossil record. And then one of the things I'm working on right now for my dissertation is describing this diversity of uh, lepidosaurs, so the relatives of living lizards. And some of these lepidosaurs that we're finding at these sites, at this site specifically, might actually be very early lizards. So one of the stories that this site is kind of telling us is the origin of living tetrapod groups, and also the origin of them living in an ecosystem alongside each other. It's the first site in the fossil record where you find frogs living alongside caecilians, living alongside very mammal-like cynodonts and lizards and early dinosaurs. Um, Another kind of fun thing about this site and many of the microvertebrate sites that we're studying in the Chinle Formation is that they the way we find them and the way we found Thunderstorm Ridge is by looking for fossil poop. The term coprolite is what we use to talk about fossil poop. And for whatever reason, these microvertebrate bone concentrations are also also concentrations of fossilized poop. And the poop could be rather large. It could be 10 centimeters long, much larger than most of the bones of the animals in these layers. And so that's the search image that we use to find the microvertebrate sites. So when I first was out there surveying the area where Thunderstorm Ridge was discovered back in 2017. What Chuck, the colleague who was with me, and I, what we saw initially was a bunch of fossilized poop basically trickling out of a layer in the Badlands. And we're like, oh, there's a bunch of poop. Might be a microvertebrate site. And we dug into it with a rock hammer. And literally the first chunk that came out, chunk of rock, it was full of big pieces of fossilized poop. And then there was a complete jaw of a trilophosauride. So it's a type of herbivorous kind of iguana looking reptile that we get in the Chinle Formation, and there was a complete jaw of one of them, which is extremely rare. And that was kind of how we first discovered the site. So the poop is what leads us to finding these sites where we find all these cool discoveries of bones.
Oh, so you were there when it was discovered?
Yes, yeah. So it was discovered by myself and Chuck Bechtal back in 2017 when we were doing surveys of the expansion land. So that's these newly added land holdings that were added to Petrified Forest National Park in the early 2000s. And so our job in 2016, 2017, 2018 was to do the first paleontological surveys of these newly added national park lands. So we were the first paleontologists really to be looking at these areas and looking for fossils. And that's how we found Thunderstorm Ridge, as well as a bunch of other sites that we haven't had time to study as much.
That sounds like a dream come true. And then for it to be so important, like what you've just described with all of the different taxa that are coming out of it, all the different groups, and what that could mean for understanding their evolution, that is amazing.
We got extraordinarily lucky, but I think what we've discovered that's maybe more important is that these what we refer to these layers of poop and bone as the coprolite layers. And what we've come to understand is that these are really where the richest fossil bone concentrations are in the Chinle Formation, and they really hold the key to understanding the total diversity of paleo environment. So prior to our work on these sites, most of the diversity we knew from Petrified Forest National Park was from large animals, dinosaurs, etosaurs, these tank-like herbivorous armored reptiles, metoposaurs, the giant salamander-looking animal. These are these large-bodied animals with large bones. They're easy to find out in the Badlands, and that was most of the diversity that we understood prior to kind of focusing on these microvertebrate sites. And now what we've realized from Thunderstorm Ridge and some other sites, and many sites that we're now just starting to study, is that this is actually pretty common. If you select these coprolite bearing layers in the Badlands and you screen wash them in the lab and look at the sediment under a microscope, what you're going to find is a huge diversity of animals, many different new species, and it's really opened a window onto what all the diversity is, not just the large animals, but also all of the small animals.
So looking at Funkus vermis then, how many specimens have been discovered in total? Is it more than 11?
Yes. So to date, we've found 95 total bones that we can confidently identify as being from Funkus vermis. And that's out of 3,044, as of today, 3,044 pounds of sediment that we've taken from the bone layer back to the lab at Petrified Forest National Park, and then screen washed to make fossil concentrate and then picked under the microscope. So we've calculated that we find one Caecilian bone for every 32 pounds of raw sediment that we collect. And that means that once we screen wash that sediment, we find one Caecilian bone for every 6 pounds of sediment concentrate that we pick under the microscope. So that's kind of the over 3,000 pounds of sediment that we've picked to find all these Caecilians is really a statement of the amount of time that's gone into this project, not just from me, but also my co-authors and the paleontologists at Petrified Forest National Park and different volunteers who have put in cumulatively hundreds of hours of time spent on microscopes just picking through the individual grains of rock to find all these Caecilians. So it's been just the fact that we were able to have all these fossils is really a statement of the team effort of everyone working for many years at the national park on this project.
Yeah, that is boring. Picking through sediment to do it for a job, which is why I started Paleocast, to just give me something to listen to. Or wishing there were things to listen to. But I guess you're all listening to Funky Worm.
Yep, well, that's
soon to be Simon and Garfunkel.
Yeah, that's the great part of it is while you're sitting there picking, you can play Funky Worm, you can play Paleocast, listen to public radio, listen to a book on tape. You can really get a lot of listening done while you're doing that kind of research. Another kind of very intriguing and mysterious aspect of the collection of Funkus vermis is the minimum number of individuals. So that's the number of individual Caecilians that we've recovered thus far from the site. We've recovered 76 individuals of Funkus vermis represented by their right lower jaws. And so this is magnitudes greater than any other site that produces caecilians in the fossil record. Most of them, only one individual is represented, but this site produces so many lower jaws and is continuing to produce them. And so it's like greatly improved the data on fossil caecilian lower jaws, and that's something that is ripe for future research for other researchers or students in the future, is to study things like tooth replacement and variation and growth from all of these different individual Funkus vermis individuals that we've collected. Another really strange thing about this is that we've found 76 right lower jaws, but only one left lower jaw. And that's a very strange pattern and is very statistically unlikely, because these animals would have had two lower jaws in life. So why in this deposit are only the right lower jaws being preserved? And it's not a factor of us like collecting only the right lower jaws, because we pick through every grain of the sediment. So if there were left lower jaws there, we would have recovered them. So this is a true signal that we're getting, that only the right lower jaws are being preserved. We don't really know why this is. We think that, one hypothesis that a colleague proposed was that caecilians, because their bodies are kind of tubular, they segregate their organs to the right or the left side of their body. And so maybe a scenario is that if a bunch of caecilians die in an event and are floating in a pond, they might all float on the same side as they decompose, because like their stomach is on one side of their body and it fills up with air. And that might create like a fossilization filter that means that only one side of their face is being preserved and the other side gets decomposed or transported elsewhere. But something very strange and mysterious is happening. We don't know what or why, that's creating this bias of only finding the right lower jaws.
In the comments on social media, put in your hypotheses. How can you end up with so many lower right jaws? What is going on?
Yep, it's really bizarre, and we find more jaws every day because we're still picking through thousands of pounds of this sediment, and we keep finding right sides. And we're totally confounded. We're not sure really how to test hypotheses with that, but something very, very interesting is going on. Yeah.
Oh, what a lovely mystery. I mean, wouldn't they be symmetrical anyway?
Like they're
right and left.
Yeah, right and left. They're symmetrical. So it's pretty confounding why only the rights would be preserved.
Yeah.
And I really don't have a good answer for it. The most possible thing is that their bodies decompose differentially on the right and left sides because their organs are asymmetrically organized inside of their bodies.
But still, if like 3/4 of your total specimens are right jaws, then you've still got the rest of the body as well. You've got the skull. You've got so much that's missing, relative to these right jaws. So can you build up a picture of what it actually looked like? Do you have a good enough understanding of its anatomy to be able to do anything with that? Or is simply the fact that you have evidence of a caecilian from the Triassic enough to be excited about?
Yeah. Well, so the lucky part is that the bones we have found are very useful for understanding caecilian evolution. So we've only found a handful of bones from the body. We've found all of the elements of the lower jaws. We've found a partial part of an upper jaw. We've found a part of a limb, a hind limb, and some vertebra. So it's only a handful of bones, but those bones tell us a lot, particularly because especially the jaw apparatus is so specialized in all other caecilians, in Eocaecilia and in living caecilians, that only a few features of that we have from like the lower and upper jaws, they tell us a lot about the evolution of caecilians, and kind of start to fill in those gaps of understanding how they evolved in a stepwise fashion.
Oh, we'll get onto that in a second.
Yeah.
But yeah, I just want to get an idea of what Funkus vermis was like.
Oh yeah.
What's its ecology? Can you figure that out from its anatomy? You've said it's got a hind limb, so that
Yeah.
sounds like similar to what you had in the early Jurassic. Is it similar to that?
Yeah, so in some ways it's similar, in some ways it's different. One of the big differences is that it likely lacks a tentacle organ. So that organ that living caecilians have, that helps with their sense of taste and smell underground, comes out underneath the eye. And There's an osteological correlate, something in the bones that we can see in living caecilians and in Eocaecilia that show us that they have a tentacular organ, and it's a groove or a fossa below the eye or in the lower part of the eye socket that basically houses this organ. But in Funkus vermis, so we found its upper jaw, which includes the lower part of the orbit where you would expect to find the tentacle organ and the groove that would house the tentacle organ. But in Funkus vermis, it's just completely smooth. There's no groove there, and so there's no sign that they had a tentacular organ like in living caecilians and like in the Eocaecilia. That's more similar to frogs and salamanders, which do not have the tentacle organ. It's also one of the several signs that we have that Funkus vermis did not have a lot of the adaptations for burrowing that later caecilians have. So that tentacle, it helps with your sense of smell and taste underground. Funkus vermis doesn't have it. Some other things that kind of point towards it being lacking a lot of the burrowing adaptations of caecilians is that it appears to have fairly large eye sockets, like what you would see in early frogs and salamanders, and pretty different than what you see in Eocaecilia and caecilians, where they really reduce the size of their eye or completely covered over in bone. In Funkus vermis, they have a large eye like what you would see in a frog and a salamander. It also has limbs. So those are all signs that if it burrows, it's not burrowing in the same way as later caecilians. But there are a few features that it has that point towards it maybe starting to evolve a burrowing lifestyle. So it's fused up bones in its jaws. And this is something that is thought to help living caecilians with burrowing underground with their head. If you fuse your bones together, your head is a much stronger, more compact element. And in Funkus vermis, it's fused. Many of those fusions that we see in living caecilians, they've already occurred in Funkus vermis. So the lower jaw is made of only two different bones, as opposed to like 8 or 9 or more bones in their ancestors before those bones have become fused up. They also have some other features that are associated with burrowing. We did histological sectioning, so thin sectioning of the lower jaws of Funkus vermis, and we found these very kind of unique canals that enter the external part of the lower jaw and then kind of end at a dead end cul-de-sac. And these little canals have also been observed in living caecilians and in their skull bones, and they house a collagen network that basically connects the skin really tightly onto the skull bone. So they have this really tight skin to bone attachment, and that helps them when they're burrowing with their head so that their skin is not slipping. These little canals in living caecilians also house glands that secrete a lubricating mucus secretion, and that kind of lubricates their head while they're burrowing. And so seeing similar canals in Funkus vermis suggests that possibly some of these adaptations, like lubricating secretions and a tight skin to bone attachment, have evolved in Funkus vermis, and maybe they are adaptations for burrowing.
Wow. Yeah, my next question was going to be, like, what does that tell us about Caecilian origins? And I mean, it can potentially tell us a lot. Like, we were talking about that stepwise evolution of this, the Caecilian kind of ecology and morphology that we have today. So does that really cement that they have come from an ancestor that was walking around on legs and not necessarily digging around as much as the modern ones?
Definitely. It suggests that the ancestral Caecilian, like Funkus vermis from the Triassic, this is an animal that looks a lot more like a salamander, and it might be terrestrial. It's not clear if the things that we see, like fusion of skull bones, it's not clear if that actually means it was a burrowing animal. And these might have been things that were in place in Funkus vermis in the Triassic that were later exapted for burrowing in an animal like Caecilia, or it's transitional. It's burrowing in some ways like later Caecilians, but in other ways it's not, and it's more similar to early frogs and salamanders. There's also the jaw apparatus is very different in Funkus vermis than it is in Caecilia. And all later Caecilians. So Caecilia and all later Caecilians have evolved this totally unique jaw closure muscle and skeletal apparatus for closing their jaws. And what they've done is that they've taken a muscle from their neck and basically attached it to the retroarticular process, which is this long process that comes off the back of the jaw in Caecilians, and it pulls down on the back of the jaw, and it causes the front of the jaw to pivot up. So it's kind of like if you yanked down on a seesaw, the front part of the seesaw would swing upwards. That closes the jaw. That is having those neck muscles attach onto the lower jaw is unique in Caecilia and all living Caecilians, and isn't seen in tetrapods outside of Caecilia and living Caecilians. And what basically all their tetrapods do is we use the jaw adductor muscles that attach from the top of the lower jaw up onto the top of your skull to basically close up and down, close your lower jaws. And so this is called the dual jaw closure apparatus in Caecilians because they have now added a second muscular group that's attaching onto the lower jaw that's closing them. And by adding in these neck muscles to close the jaw, it allows them to reduce the size of the jaw adductor muscles that attach onto the roof of the skull. And in doing that, this helps them with burrowing because the jaw adductor muscles take up a lot of space at the back of your skull. So if you can basically make them smaller, it allows you to make the back of your skull much more streamlined and bullet-like, and that helps you with burrowing. So this is this really specialized musculoskeletal apparatus that is associated with burrowing. We see it in Caecilia. We see it in all later Caecilians. It is completely absent in Funkus vermis. Funkus vermis retains the ancestral condition of jaw closure with having only attachment sites for the jaw adductor muscles that attach onto the roof of the skull. And that's something that they share with frogs and salamanders. So frogs and salamanders retain that ancestral condition. So this is one of these really big, really important anatomical features that Funkus vermis has, is this kind of ancestral morphology of jaw closure, and that's very different than what you see in Caecilia. So there's clearly a major change, not only in the lower jaw, but it also means that in the skull roof and the muscle attachments onto the skull, there's a major change between Funkus vermis and Caecilia.
Wow, it is so beautifully positioned, both in terms of the age and its characteristics for this story. I absolutely love it. Is there anything in the teeth? So we've got an
Mm.
overrepresentation
Mm-hmm.
of jaws. Are the
Mm-hmm.
teeth the same? Do we see any of those grapefruit spoon teeth, or
Mm-hmm.
is there anything
Yeah.
that we can tell about diets or something like
Yeah.
that?
So thus far, we're only finding jaws from what we think are adults, not larvae. So unfortunately, we don't know what the if the larva had different teeth, maybe like the grapefruit spoon type teeth that we see in living Caecilians that scrape the skin off their mother. We don't know if that was present in Funkus vermis. But what we do know of their teeth is that they are pedicellate, and pedicellate teeth are kind of this unique kind of tooth apparatus that you see only in lissamphibians, and they're a piece of evidence that suggests that lissamphibians form a monophyletic group. Um, and what pedicellate teeth are is that the tooth is really a bipartite structure. It's two different parts. The basal part is called the pedicel, and it's basically a hollow cylinder of dentin that's stuck onto the side of the jaw. And then the tip of the tooth is an enamel dentin bicuspid kind of sharp tipped structure that gets produced out of the pedicel. And there's what's called the dividing zone between the pedicel and the tip of the tooth. And that's kind of this area where the dividing zone, the tissue is not ossified or it's poorly mineralized, and so the tooth tips easily break off of the pedicel. They're not really attached on there very well. Um, and so this allows lissamphibians to basically keep producing these tooth tips out of the pedicel throughout their life. And the tooth tips keep falling out and then they regenerate a new one. For this reason, in Funkus vermis, we've never found the apices, the tips of their teeth. We've only found the pedicels, so that dentin cylinder that's actually ossified onto the jaws. The enamel tips fall off after the animal dies, and we've actually never found one of these bicuspid enamel dentin tooth apices. And we're not sure if that's because there's a taphonomic bias, so the tooth tips got moved, transported somewhere else, and we're not finding them, or they would be very small, much smaller than a millimeter. So maybe it's just that we haven't searched through enough sediment that's sub-millimeter to find one of these tooth tips.
Yeah, the amount of effort that it takes to find smaller things just goes up and up and up. The smaller you go, the more time it takes to
Yes,
find
yeah,
something. So, yeah, I wouldn't be surprised if it takes a whole lot longer to find one of those tooth tips.
yeah.
But we live in hope.
Yeah.
Um,
The other issue is at this site, these tooth tips should also be present in early frogs and salamanders. And we know that we're finding early frogs at this site. We also have some bones that might come from early salamanders. So even if we found one of these bicuspid tooth apices, uh, we wouldn't be able to say for certain whether it came from the Caecilian or the other lissamphibians that we find at the site. And that's been a huge issue and is part of why in our study here, we're only presenting a handful of bones that we can confidently assign to Funkus vermis. We have many other bones from this site that could be from Funkus vermis, but and representing other parts of the skeleton. They could be from Funkus vermis, but they could also be from early frogs or salamanders. And there's just not enough known about the anatomy of Triassic lissamphibians for us to confidently say whether, like the humerus that we're finding, um, or these parts of the skull roof, are these parts of the Caecilian or are these parts of these early frogs and salamanders? We don't know yet. So hopefully, as other people who are studying early Mesozoic lissamphibians, if they can find more three-dimensional complete skeletons of early salamanders and early frogs, we might start to be able to differentiate all these kind of ambiguous lissamphibian bones from the site. We might be able to say, okay, there's more anatomy to Funkus vermis than we had originally known, and these other bones are from these frogs, other bones are from salamanders. So that's kind of an issue at the site, and is part of the reason that we are only confidently ascribing a certain set of anatomy to Funkus vermis at this time.
Well, it sounds like there's plenty of work for you to do after your PhD.
Lifetime, easily.
And
more than my lifetime, yeah.
On the site that you found as an intern.
Mm-hmm.
It's crazy.
Yeah. So, yeah, the site is when my colleagues and I talk about it now, it's already spawned a series of projects, and a bunch of other students are starting to study fossils from the site. Several undergrads and graduate students from Virginia Tech here are studying fossils, and other graduate students from other institutions. And one of the great parts of it is, yes, we've picked through over 3,000 pounds of sediment under the microscope to find these 95 caecilian bones. But while doing that, we found thousands of bones from other animals, many of which are new species. So we keep picking through the sediment because we keep finding new things. And the fact that we keep finding new things tells us there's clearly more to find. So there's a lot more work to be done from these sites. Yeah.
Okay, so let's try and plug everything that we've learned now back into the higher level understanding of how all these groups are related to each other. So what does Funkus vermis tell you about Caecilians, their place within Lissamphibians, and Lissamphibians' place within amphibians in general?
Yeah, so earlier I'd been discussing how there's these many different hypotheses about what group of older animals from the Permian or the Carboniferous do Caecilians evolve from, and do other amphibians evolve from. And basically, without Caecilian fossils from older than the Jurassic, you could really only speculate which group they came from. And so by finding Funkus vermis, it extended the record of Caecilians that we could confidently say that is a Caecilian. It extended it back 35 to 40 million years into the late Triassic. And in Funkus vermis, we see a bunch of anatomical features that are shared specifically with Dicerophoid temnospondyls. And the best example of that is this animal, Dolaserpeton, which would basically look like a little salamander from the Permian of Oklahoma. And some of these kind of uncanny anatomical similarities are shared with Dolaserpeton and other Dicerophoids, and they are not shared by the other groups that had been proposed to be the sister group to Caecilians. So basically, this allowed us to exclude all these other groups that had been proposed, like stereospondyle temnospondyls by lepospondals. We can exclude them and account for why they look so much like a Caecilian is because they evolved to live underground. They have all these burrowing adaptations, and that can kind of superficially make you look like a Caecilian, but it doesn't mean you're actually a Caecilian. And so Funkus vermis, what we think is going to happen after this study is published is that it'll kind of help move the consensus towards an agreement that living amphibians, frogs, salamanders, and Caecilians are each other's closest relatives, and they have a single origin within Dicerophoid temnospondyl amphibians. And so this kind of it does several things. It tells us, first of all, it helps with the evolutionary timing of tetrapods. So before this, if you don't know how Caecilians are positioned within the tree of life, it's hard to put fossil age calibrations on molecular clock estimates for how quickly the timing of tetrapod evolution. Before, it was kind of ambiguous as to what a Caecilian is. It doesn't allow you to put these calibrations on Lissamphibia, the origin of that group. Now we have some really solid evidence as to what Lissamphibians are, and so that can kind of help us with understanding the timing of living amphibian evolution and the timing of tetrapod evolution as a whole. But it still leaves a huge gap in the record. It only pulled back the kind of oldest Caecilian by 35 or 40 million years. But as we said, that gap, that ghost lineage, was 70 to 200 million years old. So it still means that there's a long period of Caecilian evolution and the evolution of frogs and salamanders during the Carboniferous, during the Permian, where we do not have any fossils of those animals. And so it still really prohibits a lot of our finer understandings of how these groups evolved and when and where they were evolving. One of the really interesting questions that the study raised was has to do with the kind of mysterious group of tetrapods called Albanerpedontids. And not a lot of people know about Albanerpedontids. They look kind of like a salamander, and they almost made it into the modern world. They went extinct, I think, during the just prior to the Pleistocene, and they're found all the way back to the Cretaceous, and they appear to be a fourth lineage of lissamphibians. So they share a lot of features with frogs and salamanders and Caecilians, but it's not really clear how exactly they're related to those groups. They have adaptations for climbing. They might be arboreal. They also might have a way of ballistically throwing out their tongue like a chameleon to capture prey. Yeah, so there was an Albanerpedontid skull described from with soft tissue from Myanmar amber from the Cretaceous, and so they appear to have convergent feeding strategies with the ballistic feeding apparatus of chameleons. And so they're this really fascinating group. They almost survived to the present day and unfortunately didn't make it. And historically, they've been thought to maybe be more closely related to frogs and salamanders. But what we found from Funkus vermis is that actually a lot of the features of the lower jaws of Albanerpedontids are shared with Funkus vermis, so with this earliest Caecilian. And these features are not shared with frogs and salamanders. So one of the big ones is having what's called a symphyseal foramen. So it's this big hole at the very end of the lower jaw of Albanerpedontids that would have been basically filled by cartilage, and the cartilage is not fossilized, so it's left as this big hole at the end of the jaw. That is not present in frogs and salamanders. It's ossified. It's called the mento-caecilian bone, and it is ossified and gets fossilized. Also in Caecilians, Eocaecilia and all later Caecilians, the mento-caecilian is also ossified, so there's no hole at the end of the lower jaw. But in Funkus vermis, it has this hole, this symphyseal foramen at the end of the front end of the lower jaw. That's something that's shared with Albanerpedontids. And so that's one of several features that we noticed from Funkus vermis that are shared with Albanerpedontids, but not with other lissamphibians. And so in some of our analyses, Albanerpedontids actually came out as the sister group to Caecilians. And so what it points towards is that this fourth lineage of lissamphibian evolution, they might actually be the sister group to Caecilians. But kind of like Caecilians, there's possibly 150 million year plus gap in the early record of Albanerpedontids. So there's this huge ghost lineage preceding the Cretaceous, in which we don't have fossils of these animals, but they should exist. And so that's a big thing that the question that the study has raised is, could Albanerpedontids possibly be the sister group to Caecilians? And what does a Triassic Albanerpedontid look like? Does it look a lot more like a Caecilian? Does it look more like a frog or a salamander? So it really raises this big question about what are Albanerpedontids?
Yeah, and to conclude, I was going to ask, is there any more work that can be done? And yeah, lissamphibians need sorting out by the sounds of it. And it sounds like there is going to be research for centuries? Who even knows?
Yeah. So one of one of the things that this study kind of highlighted for us, looking at our study, but also looking at all other times that people have found fossil caecilians, the 11 other times that they've been found. 9 of those 11 times, the fossils were found through screen washing. All of those occurrences were found near the paleotropics in sediments that were deposited in humid, high precipitation climates. So this kind of like has created what we think might be a search image for other people to actually look for fossil caecilians, because we certainly were not looking for fossil caecilians. We found this animal purely by accident. We definitely did not expect to find them at all. It was not on our radar. And I really doubt that anyone else who has found fossil caecilians was ever looking for them. You find them accidentally when you're looking for other animals using screen washing. And but by looking at this data from our study and other studies, it suggests that there's a common pattern. And if other people reproduce this pattern, you might be able to actually look for fossil caecilians and find them. And that's targeting rocks deposited near the paleo equator in humid climates and using screen washing methods and sorting sediment under the microscope. And we're starting, my research group here at Virginia Tech and at Petrified Forest National Park, we're starting to sample a whole bunch of new Triassic microvertebrate sites that were deposited in these humid equatorial settings from Virginia, from Texas, from New Mexico, and from Arizona. And so we think it's very likely that we're going to find more Caecilian material by studying these other sites. We think it's pretty unlikely that they only occurred at Thunderstorm Ridge and none of these other sites that we're just starting to study.
Oh, for sure. And if there's one thing that I would like the legacy of this interview to be, is to, inspire someone, if they're a paleontologist, to look for Caecilians, if they are a student, to get into looking at this group as something to study. So what could you say to any one of those people to encourage them to be looking for this stuff?
Yeah. So I just generally, I encourage people to look for the small animals. They're the ones that are most often overlooked, and oftentimes they're the bulk of the diversity of an ecosystem. And that's what we've really realized from our work at Petrified Forest National Park on Triassic microvertebrate sites, is that for over a century, people were studying all the large animals and they were missing most of the picture of the diversity. So if you use these methods, if you use screen washing, if you look through all of the sediment under a microscope, you are much more likely to fill out the rest of the ecosystem. And you might find these really rare groups, things like early frogs, salamanders, caecilians, early lizards, early mammals. These animals are all in the Triassic. They're all small-bodied. One of really the only ways you could find them oftentimes is through screen washing. And so not only may you find caecilians, but even if you don't find them, you're probably going to find other things that people really didn't know much about at all. It really appears that previously we'd really only scratched the surface of what these Triassic microvertebrate sites represent in terms of tetrapod diversity. There's also a hell of a lot of work just to be done on living Caecilians. We know very little about them. They're the least understood of all living tetrapods, mostly because they live underground. And there's so much work to be done on their biology, on their anatomy, and their development. And we just really know so little about them. And also for the fossils that we've recovered of Funkus vermis, there's a lot of work that could be done just on them in ways that are totally novel, because we never had a data set with so many bones of Caecilians from any fossil site from the whole fossil history of Caecilians. No other site has produced so many bones, so many multiple jaws of the same species. And this is really ripe for someone to study the growth, the tooth development, and many other kind of aspects of early Caecilian and lissamphibian evolution. And I'm kind of moving on to studying the lizard relatives and other fossils from these sites. But I'd really love to get someone who's interested in like the ontogeny of Caecilians to work on these jaws.
Well, I'm getting the impression then that this is not the last that we're going to hear about Thunderstorm Ridge or with you. So thank you so much for coming onto the show today and sharing your research with us.
Well, thank you so much for having me.
Paleocast was brought to you by Dave Marshall and Liz Martin Silverstone, with contributions from Tom Fletcher, Vish Venkat, and Elsa Pancharoli. Music was composed by Patrick Kendall Smith. Paleocast was made possible by funding from the Paleontological Society and the Paleontological Association, but the show now relies on funding from you, the listeners. So, if you've liked this episode, please consider donating, and thanks to everyone that's helped out so far. Please visit paleocast.com for the supplementary material to this episode and for our archive of past programs, and follow us across social media platforms to get all the latest news. Finally, if you enjoy our podcast, then please explore all of our video content on YouTube and follow our other projects, the Virtual Natural History Museum and the Paleocast Gaming Network.